Hello, and thank you for listening to my contribution, which is titled Reheating and Dark Matter Production. It is a mostly qualitative summary of the research that I have done along the years with many great mentors and collaborators. Our goal is to determine the effect of early universe dynamics on the production of dark matter. I will begin by reminding you that an early period of exponential expansion, known as inflation, is necessary to set up the initial conditions of our universe. During it, the scale factor A grows exponentially and the expansion rate h is approximately constant. In its simplest incarnation, inflation is driven by the classical rolling of a scalar field phi on its potential. The dynamics are described by the set of Friedmann equations that determine the expansion rate h in terms of the energy density of the inflaton field, which in turn depends on the pressure and the expansion rate itself. For the scalar field, the energy density and the pressure are given by the sum and the difference of the kinetic and potential energies, and the Friedmann equation is equivalent to this Klein-Gordon equation with a friction term that is dependent on the expansion rate. For a sufficiently flat potential, this results in a slow roll phase of the field away from minimum, which is the inflationary period, and a subsequent epoch of damped oscillations about the minimum, which is known as reheating. The time dependence of these oscillations is of course a function of the shape of the potential. For a quadratic minimum, these oscillations are quasi-harmonic, while for higher powers of the field, these oscillations are anharmonic. We will have in mind potentials of this form. B goes like phi to the power k, where k is a constant exponent. We will be interested in timescales much longer than the typical oscillation time. Averaging out the dynamics over these short timescales, the monomial nature of the potential allows us to rewrite the mean pressure as a function of the mean energy density, and therefore allows us to solve directly the Friedmann equation for the later. The solution has this form in terms of the scale factor A for any k, that is, it scales with a to the power minus 6k over k plus 2, which, and the scale factor in turn can be approximated as a function of time, like this, so t to the k plus 2 over 3k. For k equal 2, the universe then redshifts as if it was dominated by pressureless matter, while for k equals 4, the universe redshifts as if it was dominated by radiation. We note here that the instantaneous energy density is related to the envelope of the oscillations of the scalar field. The accelerated expansion during inflation leaves the universe in an empty cold state. The energy stored in the inflaton oscillations must therefore be transferred into matter and radiation to populate the universe. Here, we will assume that the inflaton decays at tree level to a pair of fermions, which implies that its decay rate gamma phi will be proportional to the square of the corresponding Yukawa coupling and proportional to the effective mass of the inflaton condensate. This effective mass is nothing, the square of this effective mass is nothing but the second derivative of the potential, which on long time scales can be shown to be proportional to the k plus 2 over kth power of the energy density, and is therefore a function of time for a non-quadratic potential. Adding this coupling, a set of coupled Boltzmann-Friedmann equations can be constructed here. The time-dependent decay rate couples the inflaton energy density to the corresponding radiation energy density. Here, radiation stands for any relativistic degree of freedom coupled to phi, in this case, f. Now, this plot here shows the numerical solution for the system. The continuous lines show the evolution of the energy densities, the gray one for the inflaton energy density, the orange one for the radiation energy density, for k equal 2 for a quadratic potential, while the dashed ones are for k equals to 4. We note here that at T equals to T reheating, the end of reheating, which is parametrically related to the decay rate gamma, there is a crossover between the energy densities, and therefore the universe transitions from being dominated by phi to being dominated by radiation. We note that for k equals to 2, the decay of the inflaton is exponential, while for k equals 4, or in fact for any k bigger than 2, this decay is power-like. The relativistic decay products of the inflaton will interact with each other and eventually reach a state of thermal equilibrium. Their temperature will then be a function of the energy density, following the usual thermodynamic relations. The time dependence of this temperature during reheating is affected by the cooling due to the expansion of the universe and by the heating due to inflaton decay. This plot here shows the evolution of the temperature with the scale factor for k equals to 2, 3, and 4, demonstrating that for a given inflaton matter coupling, a drastically different thermal history during reheating is obtained, in particular with reheating ending much later for larger k, for non-quadratic potentials. Note here that assuming instantaneous thermalization, two particular values of the temperature can be identified. One is a maximum temperature of the universe, which we call Tmax, and the other is the temperature at the end of reheating, which we denote as T-reheat. Now, in a realistic setup, thermalization is of course not instantaneous. The inflaton decay products are initially produced at very high energies, of the order of the inflaton mass, and through elastic and inelastic scatterings and decays, they eventually reach kinetic and chemical equilibrium with themselves, when the rates for these processes can compete with the expansion rate. It turns out that thermalization proceeds by the initial population of a hard sector with momenta of the order of m phi, which through the emission of soft radiation populates a soft sector that rapidly reaches thermal equilibrium and is eventually capable of slowing down the most energetic decay products. So in this plot you can see the mean momentum for the hard sector, for the soft sector, which they eventually merge into following just the usual thermal curve. For k equals to 2, the thermalization timescale is known, and it depends on the mass of the inflaton, its width, and on the gauge coupling strength relevant for the emitted radiation. With this picture of perturbative reheating in mind, we now proceed to study the implications on the production of dark matter. Dark matter produced from thermal freeze-out, such as WIMPs, is assumed to be initially in thermal equilibrium with the standard model, and is therefore independent of any early dynamics. However, if the couplings of dark matter to the standard model are sufficiently suppressed, it is produced out of equilibrium. Examples of these out of equilibrium production processes include production through heavy mediators, in this case with a cross-section that scales with the square of the center of mass energy, written here as the Mandelstam variable S. It can also occur due to coupling suppressed by higher order operators, or through a combination of both. It turns out that if the production cross-section scales with a positive power of the center of mass energy, dark matter is always out of equilibrium, and it is produced then at the highest possible energies. That is, it is produced during reheating. Given a model, the determination of the corresponding relic abundance for dark matter follows a simple recipe. One needs to integrate the Boltzmann equation, ignoring dark matter annihilations which are suppressed. This resulting collision term depends not only on the production cross-section, but also on the phase space distribution of the parent scatterers. The evolution of these distribution functions is non-trivial. They begin with in a highly non-thermal state with momenta of the order of the inflaton mass, and it is only after complete thermalization has been reached that they take their usual Fermi-Dirac or Bose-Einstein form. Assuming instant thermalization, we have been able to derive the dependence of the dark matter closure fraction omega on the shape of the inflaton potential, in this case parametrized by k, the exponent k, the coupling to matter and radiation of the inflaton given by Tmax and T reheating, and the production cross-section here parametrized by the exponent n. What we obtain is, well, this relatively complicated expression that qualitatively tells us that the production of dark matter can be sensitive to the dynamics present at the very earliest stages of reheating, demonstrated here by dependence on the temperature Tmax. Here are 3 plots showing contours of the observed dark matter abundance as a function of K and the ultraviolet and dark matter masses, the ultraviolet scale lambda and the dark matter mass. We note here the relevance of the potential shape and the dependence on early dynamics. This plot shows the results for n equals to 0, this one for n equals to 2, and n equals to 6. And one can see the spread between the cases k equal 2, 3, and 4, which, depending on the value of n, can even switch places. The bending of some of these curves, as demonstrated by this purple curve here, is related to the fact that if the reheating temperature is too low, dark matter can only be produced at very early times, even if production is not dominated at Tmax. And this is only coming from kinematic considerations. Accounting for the finite delay in thermalization, even more interesting results are obtained. Here, I'm showing a particular case corresponding to a high-scale supersymmetry breaking scenario in which the masses of the SUSY partners are all above the inflaton mass scale except for that of the gravitino, which is the dark matter particle here. It corresponds to an n equals 6 case. Therefore here, the production cross-section has a very steep dependence on the center of mass energy, and as this plot is showing, the highly non-thermal population that exists right after the end of inflation produces far more dark matter than any thermalized radiation, even assuming that it thermalizes instantaneously. So here we see the results from ignoring dynamics during reheating, ignoring the finite thermalization timescale, and the results accounting for it, which are many orders of magnitude bigger than the naive instant thermalization results. Not only these, but we have also shown that for a quadratic minimum, at least, this is the case. I mean, dependence on the thermalization timescale occurs for any cross-section that grows with a power n bigger than 2. The relic abundance is then sensitive to the mass of the inflaton and, of course, as I mentioned, to the thermalization timescale, making dark matter an interesting probe of reheating dynamics. Now, of course, for dark matter to play the role of a probe, we must be able to detect it first. As one can imagine, the direct detection of these feebly interacting dark matter particles is at the moment impossible. Nevertheless, indirect signals can be almost equally powerful probes. Here I show one example corresponding to a spin 3/2 dark matter candidate, psi, which couples two radiation, F, and right-handed neutrinos by means of this Planck-suppressed operator. In this case, scattering cross-sections grow with a fourth power of the squared center of mass energy, making the relic abundance a probe of the reheating temperature given a dark matter mass and a value of the coupling. Okay. Moreover, this dark matter particle is unstable. It decays, producing gamma ray and neutrino monochromatic signals that can be detected at observatories such as Fermi or IceCube. Note here then that a given signal immediately determines these three parameters at once. We can also place constraints on the dark sector from structure formation by looking at Lyman alpha absorption from distant quasars. In this case, the phase space distribution of dark matter, which is not that in equilibrium, and which depends on the production mechanism, determines the cutoff in the matter power spectrum. So here I'm showing a few examples: dark matter produced thermally and non-thermally during and after reheating. More precisely, we can use these distributions to construct the transfer function of the matter power spectrum to map it into the well-known bounds on warm dark matter, and therefore obtain a rescaled lower bound on the mass of any dark matter candidate produced out of equilibrium. These bounds depend, again, on the reheating dynamics and the production mechanism, and can vary by many orders of magnitude. Of course, many more things can be said about dark matter production during reheating. We know how dark matter is produced in anharmonic potentials, but only for a two-body fermionic final state. However, the inflaton may decay in more complicated forms to matter and radiation, be it through gauge couplings, many-body final states, or at higher order imperturbation theory. Moreover, the dissipation rate of the inflaton must also be sensitive to the hot thermal plasma that is present while it decays, leading to non-ignorable in medium effects. We believe that for anharmonic potentials, these effects play a crucial role. Finally, here I have only talked about perturbative dynamics of a spatially homogeneous field, phi. However, non-perturbative effects connected with the short timescale oscillations and to self-interactions can lead to field fragmentation, which would make our study much more complicated, but also much more interesting. Thank you for making it to the end of this talk. If you want to know more, please consider having a look at these references. Thank you.